So yes, combining all those approaches to reduce embodied carbon in the concrete while at the same time ensuring durability. That's absolutely essential in our community.
All righty. Thank you for joining me, Professor Lee, for this interview, Rethink Concrete, which is part of the 20-something minute series from the OpenAir Collective. Just to begin, we'll introduce ourselves. I'm Lucca Henrion. I'm a research fellow in the Global CO2 Initiative at the University of Michigan. And I'm lucky to be joined today by Victor Lee, who's the E. Benjamin Wylie Collegiate Professor and James R. Rice Distinguished University Professor at the University of Michigan within the Department of Civil and Environmental Engineering. And he's also the director of the Center for the Low Carbon Built Environment. Obviously, you carry a lot of names with you, so I'm sure you're very busy. So we're really happy to have you join us today. And with that, maybe we can jump into some questions.
Thank you for having me here.
Of course, yeah. So as we begin, I think one of the most important things that we'd like to know is, why are low carbon building materials essential in the reduction of global carbon dioxide?
Well, building materials that includes large classes of concrete material, wood, steel, and so on, they actually represent the majority of materials we use in engineering our world. Just if you think about concrete, it's more than 80% of all the engineering materials we use. And cement goes into concrete, and we all know that cement in this production process creates carbon dioxide. So there is a lot of concern, rightly so, with regard to cement in concrete being consumed at such a large amount.
Yeah, I think one of the questions that we have is, how do you draw focus to embodied carbon versus sort of operational carbon, which is something that most people probably think about as the emissions within a building?
That's actually an interesting question. So buildings are big products to begin with. If you think of buildings as a product compared to like a computer is a product, furniture is a product, like the chair I'm sitting on is a product. But among all products we use, buildings are big. They use a lot of material. So we have to pay attention to the embodied carbon. Now, not to say that the operational carbon is not important. I think they are equally important. And frankly, Lucca, the way we move forward in reducing carbon, we need to address both the embodied carbon as well as the operational carbon. Now, back to your question, how do we draw attention to that? So I could imagine at some point in time, buildings would be tagged or labeled with a embodied carbon number attached to each building. That would be a way to disseminate information about not just the cost or other performance indexes related to that building, but also the carbon performance. So for buildings, we already have somewhat of an international competition on which building is taller and how the height of buildings grows with time. We might have something like this in terms of carbon labeling for buildings.
An international competition for the lowest embodied carbon buildings.
Yeah, something on that order. We may have to think harder in terms of how to normalize different buildings have different application, occupancy, and so on. But those are the details that needs to be worked out.
Yeah. Obviously, the way that we reduce the embodied carbon then is within the sort of materials that we use. Can you give us a little bit of insight about how you have been sort of rethinking concrete and cement and how that might actually help us achieve these, the lowest embodied carbon buildings in the world?
Yes. So the traditional way to think about concrete, when people talk about concrete or quality concrete, they think about compressive strength. And over the last maybe 10, 15 years, people are beginning to pay attention to the fact that strength is not enough, but we need to think about durability. And that's correct, because especially in the US, a lot of our infrastructures as I believe there's a piece on CNN that describes U.S. infrastructure crumbling as the headline. So we are facing a lot of challenges to that. But interestingly, Lucca, durability or the lack of is tightly connected with the repeated maintenance, which is a consumption of materials and emission of carbon. So that's where the operational carbon also comes in as well in terms of repeated repair of infrastructures. So the way I think about it is that we need to encompass strength, of course. We need to have enough resiliency. We need to have enough durability, but we also need to embody the idea of reducing embodied carbon inside concrete material. And how we can accomplish that is in fact the challenge for our research community. How do we innovate carbon in such a manner as to reduce embodied carbon, also make it durable and resilient? That's exactly how we frame our own research. You might have heard of bendable concrete. That's how bendable concrete comes about.
So you're trying to increase the durability of the concrete and then also store, I'm assuming, CO2 or storing CO2 within that concrete. So what are some sort of mainstream methods to reducing CO2 or storing CO2 in concrete?
So there are many different approaches, but I could think of maybe classifying them into three groups. One is simply reducing the carbon in the ingredients that are used to make the concrete, whether we are talking about the binder side. So the ordinary Portland cement is now often replaced, at least partially, by pozzolans or supplementary cementitious materials, SCM, greening the binder, but also looking at the aggregates as well. So those combine together to make the concrete. Now that's reducing the emission of the ingredients that goes into making concrete. You can also think about, that's the other class, is to sequester carbon, either directly into the concrete, that's one way to achieve that, to sequester that directly into the aggregate, I want to say, or sequester into the binder part. Okay. And on the sequestration of carbon in the binder part, that is the third approach, which is during the curing process. Okay. So carbon curing can help in terms of reducing the amount of cement usage. And all those three can be effective to different degrees. Now, there are advantages and disadvantages on each of those. And that's where the research needs to go. How do you optimize all of those in a single concrete material so that you maximize the reduction of carbon?
Yeah, that's really helpful to think of those three different ways. Do you have any details about sort of what some of the advantages and disadvantages are of, I think specifically curing with CO2, which is sort of becoming a mainstream method that's in the market at this point?
Well, all of them are used actually, and and you're right that there are advantages and disadvantages. So in terms of directly curing concrete with CO2, that is typically done for precast concrete as opposed to cast in place, because you need a reaction chamber in order for the reaction to take place. Basically, reaction is a conversion of the gaseous carbon into carbonates. So it's a mineralization process. It turns the CO2 gas into calcium carbonate, for example, okay, inside the concrete. That becomes a solid inside the concrete and is permanently sequestered. Okay. Now, the challenge for that approach is that the curing is a diffusion process. So you can carbonate the surface layer But once it gets carbonated, it blocks the carbon dioxide from entering further. So there is a limit as to the thickness, for example. There are some processes that requires carbon to go through the whole thickness in order to turn the powder into a strength-bearing solid. And that puts a limit on the dimensions, the size of the structural element that can be built with such a process. So there are some limitations to that. There are ways to optimize in terms of the conditions under which this carbonation curing process takes place, such as humidity control, temperature, pressure, and so on. That's part of the research that we are also doing in our lab. There are other groups also working on this. Size limitation is basically the main limit based on carbon curing process. Now, there are also processes that people directly inject carbon into a ready-mix truck, and idea is to have that carbon mineralized during the mixing process. That is quite appealing. The amount of carbon that can be sequestered in that process is somewhat limited at this point in time. So when we talk about this carbon sequestration, we also need to think about the energy and cost to advance that process versus the actual amount that can be stored in the concrete material and how much escapes without being stored. Right? So there are technical challenges, but there are also incentives that can help overcome those challenges. One of those challenges I forgot to mention would also be the cost of the carbon itself, the capturing the carbon. That's not a simple part. It's actually something in practice we need to account for. There is also a cost to that process. And, how do you reduce that process? Can we make use of flue gas directly as opposed to pure CO2? So there are lots of challenges there, but there are also incentives that may help us learn more and motivate us to do a bit more, even as we are start on the beginning of this road to carbon sequestration in concrete, such as the Q45. There will be providing some financial incentives. Some cities are already beginning to have low carbon code for their buildings in their jurisdictions. So the policy tools are, to me, as important as the technical tools to drive this forward, to make it a reality, to be able to really capture a significant amount of carbon and lock it up in concrete buildings.
Yeah, I think the OpenAir people will be really happy to hear that policy is a very important component of that as well.
They have to go hand in hand.
Absolutely.
There's no question about it. You have to remember, Lucca, that the industry that we are talking about is relatively conservative. So any help from the technical side as well as the policy side to move it would help with the industry adopting these innovations and technologies.
So you mentioned at some point CO2 storing aggregates. Do you have any more information about that? That seems to me to be a really exciting opportunity to be able to sort of replace part of the aggregate with stored CO2.
Well, there are some natural materials and some not so natural materials, industrial waste streams, for example, that could be reactive to CO2. And we can pre-carbonate those ingredients and then use them as aggregates inside concrete. After all, aggregates in normal concrete is basically a space filler. It's a filler. It makes concrete less expensive because the aggregates are less expensive compared to cement. There are other reasons also
Sure. Sure.
besides economics, but that's one major part of it. So if we can make use of that part to lock up carbon dioxide, why not? We can do that. So there are there are industrial waste streams that can allow us to do that, and we are actually doing it in our laboratory. Some of those commonly known ones are fly ash, for example. Not all of them, but some parts of fly ash. Slags, for example, they can be pre-carbonated before they are used as aggregates inside concrete.
So I know that fly ash is also used as a supplementary cementitious material. You were talking about SCMs earlier. When you try to use it as an aggregate, does it no longer work? Like, is it being used as an aggregate and not an SCM, or can it play both roles? Can it be a hybrid?
There is no reason why not. So in some situations, when the fly ash content is high enough, they are not all reactive. So they in that situation, they just stay as fly ash inside the concrete material. So it becomes a filler, if you want to think of it that way. One can extend that thinking further to even low water cement ratio concrete, where the cement content is high. A lot of high strength concrete are made that way, low water cement ratio. And a lot of that Portland cement are not necessarily hydrated. They just sit there inside as solid particles. In a sense, they are just expensive fillers.
Okay. I think that's
to answer your question, yeah, fly ash can be used.
It can be both. Okay.
Yeah.
Okay.
No question.
So I think, with these sort of three different methods, talking about carbon curing, carbon aggregates, and then affecting the sort of cement content in your concrete. Do you think there's potential for a carbon negative concrete? Do you think there's an optimal solution that would allow that to happen? And what would that take?
That's an interesting thought. That's actually exactly what we are trying to do, to bring all three approaches together into a single material to drive to carbon negative. But we are doing that not only for ensuring a low carbon concrete. As I mentioned earlier in this discussion, we are also trying to make sure that it's very, very durable. Okay? So that's one of the challenges we need to pay attention to. When we do carbon sequestration, when we use low carbon ingredients, all of those things, there are potential penalties. And we don't want to penalize the durability aspect. That is something our community needs to pay attention to. So you don't want to lock up carbon in concrete, which needs to be repaired every year. That would definitely not be very sustainable. But we go beyond that. We actually make concrete that are ductile, so that even if you overload it, currently the most common form of deterioration in infrastructure is cracking. There is no lack of compressive strength. Most of the time you don't fail because of excessive compressive loading. No, it's mostly cracking. Cracking is tension. So that's one major effort we are putting in to enhance durability, is to make our concrete resilient to tensile loading, so that you can damage it, but it will never fracture into pieces. It actually heals itself. And that's a big part of the equation in my mind in terms of reducing operational cost. So yes, combining all those approaches to reduce embodied carbon in the concrete, while at the same time ensuring durability, reducing operational cost.
Which also
essential. That's absolutely essential in our community.
Yeah, which also plays a role, right? The durability, then the lifetime over which you're doing things will be extended, and then you have sort of your per year embodied carbon sort of goes down based on the amount of time that you can go.
Right, exactly. So the community is more and more embracing life cycle analysis. And the life cycle analysis begins with the material production, but it doesn't stop there. You have the design and construction and use phase. The use phase can be easily 25, 50, 75, even 100 years. So that's a peculiar thing about infrastructures and buildings compared to other products we talked about earlier. They are big, they use a lot of material, and they stay around for a long time. Some people call our infrastructures monuments. Monuments, they stay there for a long time. So what does that mean? It means large material flow. It means potentially repeated repair requirements if we are not careful.
Yeah. I think concrete is definitely the thing that we see, the really extended lifetime of. I think we talk about Roman concrete still being around thousands of years later. I think with that, the idea that concrete is still a place where a lot of innovation can happen, and there's a lot of movement that can happen, makes it a really exciting opportunity. I guess my sort of last question would be, how do you imagine the concrete industry will adapt to new technologies and change over the next, couple of years or the next 10 years, as research brings forward these really amazing solutions? How does the industry adapt to that?
So when you talk about concrete industry or concrete construction industry, it's actually quite complex. There's a whole value chain from the financiers to the developers and the builders, the owners and the users, all connected together. And then within this chain, there is the AEC community, the architecture, engineering, construction community, the material suppliers, and so on. So they all play a role, right? Different roles, and somewhat connected to one another in the value chain of construction. And in my mind, I really believe that it's not enough to focus only on the material. Certainly not just cement, certainly not just concrete, but we need to extend that to the design phase, right? To thinking about how to design buildings that have low carbon, that have low embodied carbon and operational carbon. And I think there are more and more owners who are asking for that. So I heard that Microsoft have expressed a desire to reduce the carbon, the embodied carbon and operational carbon in their buildings, in the data centers. So owners are asking for that, and I'm sure users are also wanting to be able to. We need buildings, but we also want our good natural environment. So we want to harmonize those two, the built environment and the natural environment. The key question here, that the key challenge in my mind that we are facing, is how do we bring all these parties together and align their common interests and rapidly move us and transition to a low carbon economy with low carbon building. How do we do that? That's exactly, by the way, if I may put a plug for my center on low carbon built environment, that's exactly what we are trying to do, to build a platform where we can bring all these different entities together with the common goal of reducing carbon in the built environment. And I believe that the industry is moving in that direction. We just need some help to glue those different pieces of the puzzle together.
Alrighty. Well, with that, I think we've covered a lot of really important ground. Dr. Lee, we really, really appreciate your time. This has been really enlightening, and it's good to hear sort of about the future of rethinking concrete. Is there any last things you'd like to say before we end this interview?
Well, I would say that we have a lot of work in front of us, and we need the help from all areas, every part of the value chain of construction, and partnerships between industry and academics and agencies and public sector and private sector. All those are necessary because the carbon problem, the climate challenge is big and is urgent, and we need to take action now.
And that's especially important with infrastructure, which may be something that we're stuck with for a very long time.
Absolutely.
Alrighty. Well, thank you so much for your time.
Thank you, Lucca.